So section 3.1, derivatives of polynomials and exponential functions. Because if you are watching the video, you can pause and understand the proofs better, but I'm going to have to run through them way too fast. So, derivative of a constant function. The best way to look at it is through the picture that you can see right here, the picture proof. If you draw the function y equals a constant, you are drawing a horizontal line. Its slope is 0. The formal proofs take you through the limit as h approaches 0 formulas, and you can see how very quickly you get 0. Then, hold on. We got to, the power rule. Super, oh my gosh, you don't even know how much you're going to use this. No idea how much you're going to use this. So if you have variable x and n is a particular constant, then the derivative of x to the power of n is n times x to the n minus 1. So, quick question. What then is the derivative of x to the power of 5? I'm going to check chat. What is the derivative of x to the 5th power? You got it. 5x to the 4th power. Yes. Now, I spent way too long putting this together, but anyway, this is really powerful right here. If you remember binomial expansion, this is the idea of binomial expansion with underlines where numbers come into play and bold number ones at the ends to show that you're dealing with a row of Pascal's triangle. Whatever number n represents, you are looking at the nth row to fill in those blanks, as you can see over here, for if n is equal to 4. And if you remember, you've got in your binomial term 1, term 2. You start off with term 1 to the highest exponent and term 2 to the 0 power. And what is any real number that's not 0 to the 0 power? A number that is real and not 0 to the 0 power is 1. Yes. I'm not going to mention the issue of 0. It's a non-issue at this moment. And then each goes down a power versus up a power until you reach the other end. Now, I wrote this out. This right here is just a notation that means in the nth row, position 2, but understand that these, what I'm going through, in fact, I should highlight, draw, highlight. These are considered position 0, just as this is considered the 0th row. So what you're going to find is the 0th position is always going to be 1. The first position, take a good look, but I'm going to change my highlight color. That is going to be the actual number n. That's very important. That right there. After that, they go into formulas, and there are different formulas that basically this means on top the Pascal's triangle row, on the bottom the position, but again understanding that we start counting with 0. Anyway, with that said, then we move on to, this is the formal proof for the power rule, provided that the n is a whole number. And this just means n is an element of the set of numbers that are the whole number system, meaning 0, 1, 2, 3, 4, 5, and so on. However, we're going to be using this rule today very quickly with non-whole numbers, but that proof can't come about until we get through logarithms and derivatives of logs. So until now, we use this, and it's a beautiful, beautiful proof. So we start off with our limit definition. And I need to, excuse me, apologize for coughing in the microphone. So I'm highlighting this minus f of x right over here is going to end up canceling with the front runner of my binomial expansion. And my binomial expansion being all of this right here. Once those two cancel each other out, look at what is left over when those two subtract away. I want you to see that for each term in here, h is a factor. So I can factor an h out of all of those leftovers. And I want to be careful to make sure that my blue highlight represents one particular thing. Erase, draw. So that blue highlight is all of this right here, but I now have factored out the h. And I want you to notice that this first leftover term after the front runner gets canceled out, once I factor the h out, I am getting something rather familiar. Because after I reach this step, I'm going to be able to kill the h, kill the h. And then I end up with just that piece highlighted in blue, but without the h. And what do you know? Somebody right there shows up that's very important, because when I plug in 0 for all of the h's, every single term has h except for that one who happened to be the second, there you go, the second term of that binomial expansion with the h factored out. Boom, power rule, powerful, beautiful. Then I need to do that so that I can now scroll, and the constant multiple rule. Constant multiple rule is different from the constant alone rule. You can take a look at this proof. It's pretty quick and straightforward. I want to remind you that there are some limit rules being applied here where a constant can be pulled completely out of the limit, and we end up back to that limit formula for derivative. Now, here's something I want you to think about. If you are asked to transform a graph by multiplying the function by a number, how does that transform the graph if you multiply the function by a number? And Grant Merritt, tell your brother to stop talking to you. Okay. What happens to a graph when I multiply it by a constant? You guys see what I'm doing, right? Right. Does that affect slope? Does that affect slope? Oh, yes. It affects slope by a constant multiple of that slope. You can see that right here in the formula. When you have a constant multiple, you just sort of throw it to the side, take the derivative of the function you know, and multiply, and magic happens. Now, here's another thing I want you to think about. If you have the graph of a function and you add a number or subtract a number to the function, how does that transform the graph? Whoop, 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 whoop. Does that change the slope at the x values? Does not change it. So it's important to understand the difference between the constant multiple and the lone constant term. But if you think about what effect that has on graphs, it makes a lot more sense beyond just these rules and looking at the algebra of the formulas. Constant multiple affects the slope, so we keep that multiplication. But a constant by itself has no effect on the slope. So that means that if I give you, let me draw, come on, wake up, wake up. If I give you y equals x cubed, oh wait, we haven't hit the sum rule. It's okay. X cubed plus 2. What is the derivative? What do you think is the derivative? Yep, 3x squared. That plus 2 has no effect on the limit. But what if I give you 6x to the fourth? What is the derivative of 6x to the fourth? Mm-hmm. 6 times 4, and subtract 1 from the exponent. Next, I have for you the sum rule, and it turns into the difference rule if you just make that addition a subtraction. I'm not even going to bother throwing at you that because you know addition and subtraction are essentially the same, just opposite operations. Appreciate this now, because I think it's tomorrow that we will be looking at the product and quotient rules. So right now, appreciate that when you are adding two functions together, you get to literally go with the two functions. What's your derivative? Oh. What's your derivative? Oh, plus. Appreciate right now that you literally just separately differentiate the functions and move on. So with that said, before I move to the next derivative formula, I'm going to give you a quick little example. Let's say I have 3x to the, I don't know, 6th power minus 8x squared plus 2x plus 5. What do you think is the derivative? I'll give you a moment. Oh, we've already got an answer sitting there. Okay. So 3 times 6, subtract 1 from the exponent, minus 8 times 2, subtract 1 from the exponent, and now it's just an understood 1 that I don't need to write. But now what about that 2x? You guys have the right answer. But I was reminded in first period that I need to take a moment to talk about that. 2x. I'm just going to have that over to the side. If I use the power rule to take the derivative, then it is 2 times 1x to the 1 minus 1, which is 0. And ignoring the issue of certain technicalities, what is any number to the 0 power? 1. That means this is 2 times 1, or 2. And you know what the quick way is of taking this derivative, which some of you probably already thought about? That's a line. That will draw you a line. What is the slope of that line? So y equals 2x. What is the slope of y equals 2x? Typo. Okay. The slope is 2. You know this. Let me draw just for a little emphasis there. So you really don't need to go through the power rule when you see a constant times x, but you also don't need an entire extra derivative rule. I'm watching chat and laughing, and I need to not. You don't need to learn an extra rule, but you are going to get to the point where you can take these derivatives without even thinking, because you've done these so many times, or at least that's where you will be in the future. And then I want to point out that plus 5, the derivative is plus 0, so you are correct. Don't need the plus 0, it's just in the way. All right, now, next. By the way, please, if I'm getting to 10 minutes left of class, tell me. I have to give you enough time for your quiz. And I'll pre-warn you as we go through some of these examples about what is going to show up. It's not bad at all. All right. Exponential functions. Exponential functions. We're going to take the derivative of an exponential function. Now, why don't I right now warn you about one of your quiz problems? One of your quiz problems is going to be written in the following way. And I'm going to write this down, and then I'm going to erase it. And I'm also going to use the letter B right now because this has the letter A in it. You're going to see on your quiz f prime of B equals, and then you're going to see some function with B plus H plugged in minus the function's value at B. You're going to see this, and you're going to type in what the function f of x is and what the number A is, or sorry, what the number B is, because I had to use B because A is sitting right there. But it'll be A on the quiz. So just as a little bit of a pre-warning, that will be one of the problems on your quiz. All right, I'm going to erase that out of the way and talk about this, because if you understand this limit, it's really going to help you with understanding the formula for the derivative of exponential functions. If I'm dealing with the function a to the x, where a is a real number and x is the variable, when I plug in x plus h, I get this. Now, using the exponent rule, when I add the exponents, it's because I am multiplying the same base to the individual exponents. So a to the x times a to the h is equal to a to the power of x plus h. Recognize that exponent rule. And then I'm going to erase those emphases. And now I want you to take a look at these two that I just highlighted, and notice that it just is factoring a to the x out of the numerator. But a to the x does not have the letter h. Therefore, the limit sees a to the x as a constant. Now, a to the x is not a constant, it just is to the limit. So I can pull that outside the limit. And I am still finding the derivative of f with respect to variable x, so I've got a to the power of x, times this limit. However, this limit is a little bit harder to work with. So what I have set up is a Desmos play thing for looking at this limit. Now know that when I turn the Desmos screen on, h is going to have to turn into x, and then we are going to look at what happens when this function with x sitting in it approaches 0. And I'm going to have to give away too many hints right off the bat because I have to get this done in an hour, actually in 50 minutes, so you can have a quiz. So here we go, right here. Now, I have a to the x minus 1 divided by x. And I want you to see if I can get it better. It's undefined if I can get it on 0. There we go, there. Undefined at 0. But if I'm really close by, the y value, the 0.5885, is about what this is approaching. But you know what? This is a limit. Okay, let's go in further and get a better. When I go in a little bit further, I'm getting a y value of, even better, 0.5878. But I can go in even closer. Now, you notice that I have the natural log of a sitting there as well. Coincidence? I think not. Now, let's change a, but in order to do that, I need to first go to the home window because this is going to change too much. So I'm just going to manually move a little bit, and you can see how the y-intercept is changing. The y-intercept of this graph is the only thing I'm really concerned about. I want to zoom in, though, and talk about a special thing. Imagine you are a mathematician pre-computer time, so you're number crunching this thing out, and you are trying to find what is this pattern to the rate of change of an exponential function with different bases. And they first, from what I understand at least, they first noticed that any one particular exponential function's rate of change was always a constant multiple of its y value. But then when you start looking at different bases, you start seeing another pattern. And while I'm not very zoomed in, the y value 0.918 and the natural log of that base number are pretty darn close. So it looks like maybe the answer to that limit is the natural log of the base. Maybe. But now I want to move a around and I want you to see it jump over 1. Imagine being a mathematician. I mean, if you're willing to number crunch this stuff, you've got some serious number curiosities. And if you notice that when you look at, say, the derivative of 3 to the x versus the derivative of 2 to the x, that one of them has the constant multiple 0.69, the other one has constant multiple 1.09, you're like, huh. Is there a base? Is there a base for which the derivative is just the exponential function itself? That's right. Take a look at this number as it approaches 1. Well, it looks like it's between 2.7 and 2.8. I wonder what number it could be. So, all this time that you've heard of the number E, you need to understand the definition of E. If you've ever seen the actual definition of E, it's always given as a limit. Why? This. It is coming from the definition of the derivative of an exponential function. They found that there is a sweet spot for the base of a function where the derivative happens to be just itself alone. And that's beautiful and it's amazing. Now, while I would like to sit here and just bask in this amazing discovery, we need to move forward. And so the answer to this particular limit is the natural log of whatever a happens to be, which means that the derivative formula for a to the x, mind you, though, if you're an exponential function, the base of a can only be positive, and it is not the number 1 to be considered an exponential function. Any other base and it's not exponential, it's something weird. We'll leave it there. So the derivative of a to the x is some constant times itself. That means an exponential function grows at a rate proportional to itself. I'm going to come back to that in a moment, but in the meantime, we are able to use that formula to get the derivative of e to the x. What is the derivative of e to the x? I'm looking in, what is the derivative of e to the x? Looking in chat. You got it, e to the x. It's so easy, it actually gets annoying sometimes. In today's homework, you're going to be using the derivative of e to the x formula. In later homeworks, the other one is going to come out, but I really feel it's important to go through this process to come to that conclusion. And so I'm trying to quick run through it to be able to get through the 50-minute lesson. Okay. Before I go into examples, though, I want to express to you how powerful the exponential function is through these derivative formulas that we have. So I'm going to ask you this. What is the, I'm going to draw. If I compare two functions, let's take 5 to the x versus x to the 5th. Okay. What is the first derivative of 5 to the x power? The first derivative of 5 to the x. Jacqueline, you're just punching the wrong keys over and over again. Don't feel bad. It happens. The derivative of 5 to the x is the function 5 to the x times a number. What number? There you go. Natural log of 5. What is the second derivative going to end up being? When you have a constant multiple, like natural log 5, you keep it. And then you multiply that by the derivative of 5 to the x, which is another natural log of 5 times 5 to the x. So with that said, do you think we can make a quick shortcut to the third derivative? and the fourth derivative. And how about just, let's go to the nth derivative. All right. Now, g of x. Oh, x to the fifth, x to the fifth. You know, x to the fifth was like, look at me. Wow, I'm so steep. And then 5 to the x came around and just shook its head at it. Because watch, what's the first derivative of x to the fifth? You probably already said it in your head. What's the second derivative of x to the fifth? You got it. 5 times 4 is 20. Bring it down 1. What's the third derivative? And maybe you see where this is going. Yep. This polynomial is doomed. The fourth derivative, and the fifth derivative, and the fifth derivative, and, the sixth derivative, 0. And what are the derivatives from then on? 0. Take that, polynomials. This should help you to understand how powerful exponential functions are. No matter how many times you take their derivative, they are still growing exponentially. So, got to keep going. More examples, because those are the rules you need to know. And eventually I'm going to have a nice little quick, here's all the rules you need to know given to you, but those are the only rules for today. I've got a few examples. Oh, I didn't get that one quite typed up yet. Oh, well. Okay, I've got a few examples for you. For problem number 21 here, with finding dy dx, I'm forewarning you, and I forgot to forewarn first period, so I need to maybe mention that on Google Classroom for them. Your textbook likes to give unknown constants without telling you. So if you look at number 21, A, B, and C are representing unknown constants. They are not the variable. X is the variable. So when you take the derivative, you're going to take the derivative thinking of them as constants. So with that understanding, what is the derivative of y for number 21? Yep. 2ax plus b. And you know, just for the fun and the sake of it, what x value makes that equal to 0? What x value will make that derivative 0? Does that look familiar? That's the formula for locating the x-coordinate of the vertex of a parabola. Now, yeah. Calculus just bypassed that formula for you. Do you see how amazing this can be? You don't need the formula for finding vertex of a parabola any longer. You just need to be able to take its derivative and solve for what makes it equal to 0, and wha-bam, vertex. All right, now, very important, you're going to run into some problems where you have division and multiplication, And you do not have a rule yet for that. That means you get to expand your algebra. If you are dividing by a lone term, you can distribute division over addition just like you distribute multiplication over addition. And let me also remind you, what is the exponent for the square root of x? Yep. So I'm going to take this and I'm going to rewrite it before I go through the derivative. I'm going to first rewrite the exponent in the denominator. But know that for today's homework, you cannot take the derivative until you have simplified to a format of number times x to a power, plus or minus number times x to a power, plus or minus a number times x to a power, plus or minus e to the x. Anyway, so now continue and distribute the division. So what is x squared divided by x to the 1/2? What is the power when x squared is divided by x to the 1/2? It is x to the 3/2 power. Plus constant multiple 4 times x divided by x to the 1/2 means this is going to be 4x to the 1 minus 1/2, right? Plus 3, but I don't want to write it as 3 divided by x to the 1/2 power. I want to write it as 3 times x to the negative 1/2 power. Oh, the 3 isn't square rooted. All right. Now this is in a format where you are ready to differentiate, so differentiate. And carefully do fractional arithmetic. 3/2 minus 1. 4 times 1/2. 1/2 minus 1. Then plus 3 times negative 1/2. And negative 1/2 minus 1. Negative 3/2. Your textbook is going to simplify, or it's going to simplify it into a positive exponented, rooted, not fractional exponented thing. What I want you to know, because I don't have the time to go through the algebra of this, is your textbook loves to simplify, crazy simplify. I want you to know the algebra that they are using, but I also know that you only have so much time in your life. Sadly, the most important thing in your homework is being able to use the rules correctly as far as the course is concerned. I think it is very valuable that you make sure you know your algebra. And if you are running out of time, I'm okay with you opening up the solution manual, looking at the algebra and recognizing it, but make sure you recognize it to get to the simplified answer. Now, I've got to make sure to get through this next little bit before you need to take your quiz. Physics, folks. What is a normal line? And how important is a normal line, oh physics folks? Where are my physics peoples? Or at least I should say those of you who have already taken physics. By the way, yes, very good, Arden. In this case, because we are sadly two-dimensional, we don't have a surface, we have a curve. But know this, if you take physics before taking calculus, while the physics may be a little bit more challenging for you because you don't have the calculus background yet, when you go to calculus, the calculus is a little bit easier because you have the physics background. Vice versa. Some of you are taking physics next year. And in that case, the physics is going to be easier, but you're going to have to try and learn the physics while you're in here that will support that class. Some of you are doing both at the same time, and I think that's a really nice combo. But, moving on, I need to talk about this. So let's say this is the graph of some function. I'm going to call it g of x so it's not the same as the function I have there. Here's a point of tangency, and I'm going to draw a tangent line. At least I'm going to try to draw a tangent line. Oh, yes! One of the better ones I've done. Now, the normal line goes through the point of tangency, but is perpendicular to the tangent line. So that means when you write the equation of a tangent line, it is y minus the y coordinate equal to the slope times x minus the x coordinate. Oh, hint. Today's quiz, you're going to write an equation of a tangent line given these pieces of information. Know how to do an equation of a tangent line. All right. A normal line, so that's tangent line. The equation of a normal line, it's still using the point of tangency. The only thing that's different from the tangent line to the normal line is the slope. And how do you perpendiculariate the slope? I'm looking in chat. Negative reciprocal. So let's do this quick example, and then I'm going to open up your quiz. We need to find the derivative of the square root of x. The square root of x is x to the 1/2. So the derivative is 1/2 x to the subtract 1 from positive 1/2. And if I write that in simplified form, I get something that, oh my goodness, we did that yesterday through the limit. Now I want to know the slope at this point. So I plug 3 in. You know what? I just realized something really silly. I wrote the point backward. I'm changing it right now. Dyslexics tie. That was for dyslexias unite, but making it. Oh no, I think it was dyslexics untie for unite. Sorry. Oh, there we go. All right. So f prime of 9 is equal to 1/6. So that means that the tangent line is y minus 9 equals 1/6 times x minus 3. I'm dyslexic again. I've often wondered, had I been tested? But anyway, the y coordinate is the 3, the x coordinate is the 9. There we go. There's your tangent line. The normal line oh, wait. No, I'm fine. Never mind. What is the slope of the normal line? -6. Ba-bam. All right, I've got to get that quiz moving for you because you've got 10 minutes left in class. I'm stopping